Okay, today's a pretty cool class. At least I think it's cool, which means maybe you won't. So it's about a different max flow algorithm, but it's going to use some of the tools we learned last week. So it's called push-relabel. So so last week we sort of did two topics, both under this header of different kinds of average analysis, so to speak. One was this amortized stuff, especially for data structures. So the idea that different operations have different time, but in the aggregate, it looks great. And the other was, some introductory randomized algorithms, where now we're taking the average over, the random bits inside the algorithm. So two different senses of the word average, but both actually still retaining that worst case, all that good worst case robust stuff that we're really interested in. So, um, so today's topic is going to be some kind of really interesting max flow algorithms, but their analysis is also kind of interesting and is going to use some of these amortized ideas from last week. So I thought it's a nice topic that sort of combines a couple different things we've been doing recently and hopefully reinforces both. Okay. Yeah, okay. So there's the amortized stuff in case you guys forgot. This was from last Tuesday. All right, so we're going to do these push-relabel algorithms. They're going to be actually, I think the fastest algorithms that we'll present in this class for flow. There's faster ones out there, but they're kind of beyond the scope of the class. All right, so I want to quickly remind us some of the ideas from the flow algorithms. So we first did Ford Fulkerson, which was just augmenting paths, and that actually was fine as long as the flow was pretty small and integral and stuff like that. But for larger flows, to get a polynomial time algorithm, we tweaked that algorithm. Instead of just taking any augmenting path, we always chose the shortest augmenting path. That simple idea was what was behind the Edmonds-Karp algorithm. So we take the shortest path, we route as much flow as possible, and out comes a strongly polynomial running time. And while I think the algorithm is very natural, maybe something you would have tried on your own if you're implementing it, the analysis was like very, at least in my opinion, subtle, right? Because it hinged on this lemma, which was focusing on the distances in the residual graphs. If you guys remember, the proof was all about like, you have a source, right? And there's some, oh, this is like 3 edges away, 4 edges away, and stuff like that, so BFS layers. And over the course of the algorithm, some of these edges get deleted from the residual graph, and other edges get reintroduced. So that distance from S to V in the residual graph may be increasing, going up and down or whatever. And the key lemma, the most important lemma, somehow was focusing and trying to show that the distance from S to V never goes down, it only goes up. Right? And that was actually like the most important observation. And that led to these arguments where like, oh, every time an edge gets deleted from the graph and reintroduced, two vertices must flip order in terms of distance from S and stuff like that. But there's all these kind of distance-based arguments in the residual graph that allowed us to get a stronger polynomial running time. Which I don't know. I mean, I feel like in hindsight, it's still not obvious. I mean, I think it's so bizarre in some ways that we're focusing on flows and the whole discussion was about distances. Right? I think that's sort of unusual. Okay. Um, so today also, um, today's algorithm also is going to have a lot of emphasis on distance, which is sort of some kind of like dual uh, interpretation. So let's see. All right. So, okay. So with that in mind, knowing that not only are we working on flow, but there's going to be something related to distances. Okay. So the push-relabel framework is going to sort of relax some of these ideas. So it's going to be a little bit of a non-intuitive algorithm at first, so bear with me. So first I'm going to just present the parts, like the pieces of data that the algorithm's keeping track of. So there's really two, okay? We have, at any time, the algorithm will be maintaining what's called a preflow. Okay, so we're still trying to solve S to T flow, But last time we were always like routing one whole unit of flow from S to T and one whole unit of flow from S to T and stuff like that. So in the middle of the algorithm, maybe it wasn't a max flow yet, but it was still a flow. Like for every vertex, what came in is what came out and stuff like that. Everything was going from S to T. A preflow is going to be like looser than that. It's going to relax. I have a more formal slide coming up. It's not going to require everything that goes in, everything that goes out and stuff like that. So the intermediate part of the algorithm is actually not going to maintain a flow. It'll maintain something weaker called a preflow. At the end, it'll arrive at a flow, but in between, it'll be something more relaxed. And the second ingredient is, so in the Edmonds-Karp algorithm, we always just focus on like the exact distance from S to every other vertex, like as if you ran BFS. And implicitly, we'll do something similar, but not exactly. What we're going to do is we're going to assign labels to every vertex that are going to kind of act like distance labels, but might not actually be the true distance from S to V for various other vertices. So these labels are going to act a little bit like distance, but it's going to be more relaxed. And these preflows are going to act a little bit like flows, but it's also going to be more relaxed. So we're entering this framework where we're kind of relaxed on some of the rules. So let me do that more formally. Okay, so a quote unquote preflow. So just like a flow, we're assigning values to edges, and you can think of the value as like how much water is going through an edge. Okay, and so the rules are similar. It's going to satisfy all the capacity constraints, first of all. So for every edge E, the amount of flow on that edge is at most the capacity of the edge. That's just like before, the pipes have like a width. There's only so much water that can go through. Okay. The second is the second part is the part that's a little bit different. Okay. So before when we're doing flow, so you have S and T, and for the intermediate vertices, we always had what goes in was exactly what goes out. That was the rule. Preflow is going to say what goes out is at most what comes in. So you're allowed to like send water in and like just leave some sitting there. Okay. At the end, we'll want to produce a flow where everything is nice and zero at all the intermediate vertices. But in the middle of the algorithm, I'm allowed to have extra water like sitting at a vertex in the middle. So I'm using this like a hat, F hat V, to be like the net flow at V, so the amount of flow going in minus the amount of flow going out. And we require that to be non-negative for every vertex that's not a source. So source, there's only flow going out. But everyone else like can swallow up some flow and stuff like that. Okay, so we're gonna like the intermediate parts of the algorithm are gonna be relaxed. They're not gonna actually have a flow all the way through. At the end of the algorithm, at termination, all the intermediate vertices will have net zero flow and you'll have a flow after all. Just that in the middle, we're allowed to bend the rules. Okay, so one component is a preflow. It's a lot like a flow, but you're allowed to have excess flow at some of the vertices. Okay. That's still good enough to define a residual graph. So for a fixed preflow, assigning water to edges, you can have a residual graph where you subtract the capacity depending on how much water you're already using. In the opposite direction, you can add that much more capacity because you could push back flow, just like before. So we still have the exact same notion of residual graphs. That's the only point I'm trying to make here. All right, so the second ingredient, which acts like distances, but is not exactly, is these labels. So the algorithm is always going to assign, like for every vertex, some value between 0 and roughly 2n, but it's going to assign an integer to every vertex. Huh? Every vertex. So just like in the Edmonds-Karp, we focused on how the distance from a V from S. Labels are going to act like that, but it won't be like exact. But let me unveil the rules. Okay, so let's see. What's number one? Okay, so rule number one is that the sink will be at level 0 and the source will be at level n, which is a little bit weird. Okay, but you can imagine, yeah, we have a bunch of layers. You can barely see them, huh? Okay, so we'll have a bunch of layers, right, which will be like all the vertices of a particular label. It'll start at 0, 1, 2, and maybe it goes on to like n, and the sink will always be at level 0 and the source will always be at level n. Okay, so two of them are fixed, and rats, I shouldn't have drawn over that. Okay, we have a nice picture coming up. Okay, so the second rule, okay, the main rule of these distance labels is that for every edge in the residual graph, it can only go down by one edge. Okay, so if we have like various vertices um, at various labels, okay, an edge can only go, if it's going in this forwards direction from a higher label to a lower label, it can only go forwards one edge, one layer, that is. In the opposite direction, you can hop over as many layers as it wants. You can have edges between the same layer and stuff like that. But if it's going this way, it can only go down by one level. Okay, that's the only rule. I know these seem like a little bit arbitrary, but we'll see how everything comes together. Okay, so that's just the rule. Any edge can only go down by at most one level. Okay. Okay. All right. So, and I have an example that we'll walk through, and hopefully we'll kind of bolt everything down and we'll understand the rules. Okay. So the algorithm. Okay, those are the kind of two objects that the algorithm is manipulating, and those are some of the invariants it has to follow. So initially, you have a source and you have a source vertex, and maybe it has some edges that are leaving it. What we do is we try to push as much flow as we can on all those edges. Okay, so that's step one. We initially saturate all the source edges in the graph. Okay, so for every edge leaving the source, I just push as much water out as possible. Okay, and I'm going to look like this. So once I push all the flow out of S, right, S will no longer have any edges leaving it anymore in the residual graph because I used up all the capacity. So all of S, the only edges that are like related to S will be going like this, from early, oh, that's the wrong way, sorry. There's only edges going to S in the residual graph. So it's totally fine to jump back or jump forward to a much higher level. It's only going the other direction, you have to go down. So, okay, so we saturate all the edges leaving S. There's only edges coming into S. So we set the level S up high at N, and we put everything else at level 0. Okay, and a lot of moving parts, so bear with me. All right. Okay, so now once I've pushed flow out of S, right? Now there's a bunch of vertices that have extra flow on it. So I've pushed some water out of S, and all those neighbors now have extra water sitting there. And my goal is to gradually, every time I find a vertex with too much water, I'm going to try to like push it to some other edge. Okay, and I'm going to keep trying to push, push, push. And my goal is eventually to try to push all that water one edge at a time to the sink. Okay, so initially I took S and I pushed as much water as I can. There's a little extra water out there. And then I might take another vertex, push some water, push some water, push some water, and hopefully I can get it to the sink over time. So whenever a vertex has extra water, has extra flow sitting on it, we call it active. Okay, so the algorithm is always going to choose some active vertex. There's a little extra water, and it's going to try to push water out if possible. Okay, so as opposed to kind of doing one whole path at a time, this algorithm is just going to do little baby steps where it just pushes along one edge at a time. Okay. Okay, so Um, okay, now there's still lots of questions to be answered. Okay, now as we kind of push flow one edge at a time and stuff, right? That in itself doesn't describe like a great algorithm. Like, oh, if you're just choosing random edges, aren't you going to go around in cycles and all this stuff, right? There's no like sense of direction to this whole like, oh, push flow one edge at a time. So we're going to add a few more rules about how we're going to do this, and this discipline will actually allow us to argue that the running times are reasonably good. So, okay, so with all those rules in place, some of which I've kind of copied in the top right corner, the algorithm will ultimately only do one of two things in every iteration. So each iteration will choose an active vertex, some vertex that has too much flow, and it'll do one of two things. I guess here they are both at once. Okay, it will push flow along a forwards edge. So a forward edge is the one that goes from like a level 10 down to level 9, or level 9 to level 8. So it will never push flow to higher levels. So if a vertex is at level 10, it can only push flow down to level 9. A vertex level 5, it can only push flow down to level 4. So we call those forward edges when it's going down one level. I forget how I drew the picture from your guys' perspective. Okay. And then, so I have a vertex, and if I can go down one level, then I can push the flow down one level, then I do. But maybe I can't because all the edges only go up or in the same level. So if there's no edges that I can push flow from down, then that means that there's no edge that's going this way. I'm allowed to take the vertex and move it up by one level. Okay, because the only rule is that an edge can't go down by two levels. So if there was an edge that went down, I wouldn't be able to relabel it because that would be two levels. But if there is no edge and I can't push anything, then I can relabel it up. And then maybe that'll take one of your edges that used to go, say, within the same layer, and now it'll be a forward edge that you can push flow on. Okay. All right, so those are the only two things you're allowed to do. Uh, oh, okay, good. I have some better pictures. Okay. All right, so maybe this is redundant with my hand waving, but it's okay to be redundant. So when I say pushing flow along a forward edge, okay, I'm picking some vertex U that has excess flow, and I'm only looking at the edges that go down one level. So it goes to some vertex V where the level is one less. Okay, and usually when I find such an edge, I'll try to push as much flow as I can. Okay, so if this has like 20 units of excess flow that I can get rid of, but the capacity of this edge is only 10, then I'll just push 10 units of flow because that's all I can do. The opposite is like, oh, if I had 5 units of extra capacity at the vertex, extra flow, but then the edge had capacity 10 or something, then at most I can push 5 units because that's all I have. So I'll take the minimum of those two, and I'll generally just try to push as much flow as possible. Okay. All right, and then the second operation is if I'm not able to push any flow along any forward edge because there is no forward edge left in the residual graph, then I'm allowed to relabel the vertex up to one higher level. So if I have a vertex that's active but there's no forward edges, then I'm able to relabel thing and I don't have to worry about this. The only rule is that forward edges can only go forward by one level. But if there's no forward edge right now, there's no risk of turning one level into two. Okay. On the other hand, by relabeling, some like edge that's sort of within the same layer might turn into a forward edge that you can then push flow. Okay, so if you think of like the sink at the bottom and you have all these vertices and the water can only go down in a way, it's like I either find an edge that goes down one level and I push flow down, or I can't find such an edge, I'll move it up to the next rung of the ladder and see if now I have a new edge that goes down. Yeah. Sure, you can choose any one you want. And maybe for here, maybe in practice you might find it useful to like always take the biggest capacity edge or smallest capacity edge or something. And I think the algorithms we analyze today won't care. Yeah, it won't matter. So every vertex always has a label at any given point. Initially, they're all labeled 0, except for the source, which is up at the top. Well, I have an example coming up, and I think it'll make all this clear. So okay. So the algorithm is relatively simple. You keep finding vertices that have extra water, and you can either push some flow out, or you can relabel it because you're not able to push it down. So just two basic steps. It's arguably simpler than like the augmenting path stuff as far as just the algorithm goes, because you're just pushing, you don't have to run like BFS and flip all these edges along the path and this kind of thing. But okay. All right. So I found that it's helpful to actually just simulate this. So let me do that. Okay. So initially everything, well, all right. So each of these gray lines represents the label that's corresponding to the number underneath. So initially I'm going to put everything at level 0. Okay. So initially, uh, we put the source at level n, which is 5, I guess. Okay. And oh no, there's 4, isn't there? Okay, good. Counting is hard. Okay, and the algorithm initially pushes as much flow as it can out of S. Okay, so it's going to send all 200 units of flow that way, and all 100 units of flow that way. Okay, and so now let me draw the residual graph. Okay, so now let's see. So X has I'll use a different color. 200 excess units, so I put a 200. Yeah, perfect. Yeah, so that's going to be addressed. Give me 1 second. Um, okay, Y will have excess 100 because I pushed 100 units of flow from S to Y. T doesn't have any excess. T will also never change. Now let me draw the residual edges based on the graph. So we have 1 unit from X to Y, and we have 100 units from X to T, and we have 200 units of capacity from Y to T. Okay. And now to get to the question, what about the edges leaving S? Aren't they going to violate? So here, because we've saturated all the edges leaving S, there's no edges leaving S in the residual graph anymore. Instead, we have these backwards edges, which is okay. So we'll have an edge like that of capacity 200 and an edge going from Y to S of capacity 100. Okay, so that'll be the initial setup. Okay, cool. This is the fun part of the lecture too, but anyway, so that would be the initial setup of the graph. Okay, so I think the key point is that an edge can only go forwards, down by 1 level at most, which is okay. It does go backwards by 4 edges, but you're allowed to go backwards as much as you want, or you can go up as much as you want. It's just that when you go down, you can only go down by at most 1. Okay. All right. So, all All right, so the algorithm only does two things. I mean, every iteration, it chooses a vertex that has some positive excess, and then it either relabels or pushes it. So I'm going to ask you guys to pick a vertex with positive excess. Any vertex is fine. Y, you said? Yes, okay, Y. All right, so Y has excess 100, okay? And then do I push or do I relabel? Yeah, so we can't push because you can only push strictly down one layer. So Y's, right now the edges leaving Y are to other vertices in the same layer. So we can't do anything with that. So we relabel it. Okay, let me redraw some stuff. So Y will get promoted up to here. And now you'll have an edge like that, an edge like that, and an edge like that, right? Okay. All right, so that would be like one iteration of the algorithm. You picked one active vertex and you tried to push, but you couldn't, so you had to relabel. Okay. All right, now pick another active vertex. Okay, X. And was X, are you going to push or are you going to relabel? Okay, so if you wanted to push, push from where to where? X to Y. So you wanted to push from here to here, okay? But that's going the wrong way. So I'm only allowed to push from here, like in that direction. So I'm only allowed to push down levels and not up levels. That's the only rule, really. Okay, so you can't push from X because it's already at level 0, so you can't go down. So instead, you can only relabel it. So X will also relabel. Um, so let me do that. We'll go like this. Then we have like an edge like that, and oops, an edge like that. This is like 100. You have an edge like that. Okay, so in the second step, we relabeled X. All right, pick a vertex that's active. Any vertex is fine. Okay, X. All right, we'll pick X again. And do you want to push or do you want to relabel? Push from, or push to. Okay, T. So now the edge from X to T does go down one level, so we can push. We'll push as much as possible. How much can I push? Sorry? 100, because the capacity of the edge is 100. So we'll do that. I'll push 100 units of flow from X to T. So what will that do? That will get rid of that edge. Now I'll have excess 100. T will have excess 100, but that's good. T is allowed to have excess. It doesn't get selected as an active vertex. And this edge now actually goes backwards with capacity 100. Okay. All right, pick an active vertex. X, okay. And then with X, do you want to push or do you want to relabel? Okay, so yeah, there's no forwards edges for X, so we have to relabel. So let me do that. Okay, now it looks like this. Okay, pick a vertex, an active vertex. Okay, we can do X again. And then what you want to do is X. You want to push or you want to relabel? Push to. Okay, we'll push to Y. Right. Okay, so this will become 99. This will become 101. Okay, so now we've pushed 1 unit of flow on that edge. And this edge is now going to go the other direction in the residual graph with capacity 1. This looks, See how the flow is gradually kind of making its way to the sink because the sink is at level 0 and we're kind of trying to push down the flow as much as possible? Okay. All right, pick an active vertex. Y? Okay. And what you want to do is Y. Do you want to push a relabel? Push to? Okay, so we'll push 101 units of flow. 101. So that will use up all the capacity on Y. This will become capacity 199. No, that's not right. Capacity 99. And the opposite direction of capacity 101. Okay. All right, pick an active vertex. X. X is the only active vertex. Do you want to push or relabel? Relabel. Okay, so X doesn't have any forward edges, so we're going to push them up. Now you get something like that, and that. And that wasn't great. And then an edge like that. All right, pick an active vertex. Pick X again. Do you want to push or relabel? All right, a relabel, no forwards edges. I have to redraw the same edges again. Okay. Pick an active vertex. Oh, what did I not do? Oh, yeah, that should be 101. 201. Thank you. Okay. It's 201. Okay, good. All right, pick an active vertex. X, do you want to push or relabel? I heard both. Push or relabel. Okay, relabel. There's no forward edges. So we'll relabel X. It goes up another level, like that. That edge. That edge. That edge has capacity 200. All right. Pick an active vertex. You want to push or relabel? Push, I heard. Push to S. Okay. Be like 101. Okay. So we've sort of like initially our goal was to push as much flow as we can out of S, right? So we just kind of dumped a ton of water coming out of S using all those edges. And over time we tried to push that down to the sink. That's really where we want to send the flow. But over time, like some of those vertices that we weren't able to push down, we had to keep relabeling, relabeling, relabeling. Suddenly it's on the other side of the source, and we just end up pushing the flow back to the source. Okay. So we've ended up being able to send 201 units of flow to the sink. Is that a max flow? Yeah, so in fact, this will give you a cut of 3 edges of size 201. Right, so we got a flow that matches the size of the cut, so it must be maximum. And coincidentally, there's actually empty layers in the graph. Like level 3 has no vertices in it, right? And if you look at the vertices on one side of the empty layer and compare it to the vertices on the other side of the empty layer, it actually gives you a minimum ST cut, right? Because X and S are on one side of the minimum ST cut, and Y and T are on the other, right? So actually an empty layer, in this case, separated, an empty layer between S and T in particular, separated a minimum ST cut. Okay, so it's very funky. Okay, so it's a miraculous algorithm, right? At least for the simple four vertex example, this like weird rule of like keep pushing down flow, but one level at a time, or else relabeling actually solve this flow problem. Okay, it's like I don't know how people came up with this, but anyway. All right, good. All right, so you should have many questions about the algorithm. A, we're just maintaining a pre-flow and pushing and relabeling and stuff like that. Do we ever actually compute a normal flow, let alone a maximum flow, right? Another question might be the running time, right? Does this algorithm ever end? Like keep like randomly pushing flow around and stuff like that. It's not obvious this algorithm terminates, let alone will terminate in polynomial time. And I guess, oh, that's the third question. Right. Okay. So the point is that this algorithm is absurd, right? The logic is not as clear to me as like augmenting path. Then I can clearly see, oh yeah, I'm sending flow all the way from S to T, and that's a good thing, right? The logic here is like, I'm not sure that like one edge at a time helps, right? And terminates and stuff. So let's try to show that. And it's actually going to be the fastest algorithms we get in this class. It also works very well in practice. Okay. All right, so here's a lemma that helps us understand what a preflow is. So again, a preflow, the only rule is that compared to a flow, intermediate vertices can take in extra flow. Okay, so preflow might be like, oh, from S, maybe I'm sending like 4 units here, one here, uh, something like this. Maybe the flow never even makes it to T. So the excesses would be like, oh, this has excess 2 because 4 is coming in and 1's going out. This has excess 1. This has excess 0. This has excess 2. This has excess 1, and this has excess 1 or something, right? So in this kind of picture of a preflow, some of the flow is getting absorbed at the intermediate vertices. Okay. All right. So the claim is that I can interpret F as some kind of like path packing, like I can decompose it into paths obeying the capacity constraints, where the total number of, or the total quantity of paths for each intermediate vertex V, the number of paths from S to V is the excess. Okay, so I'm saying that I can take like this picture and I can break it down into like 2 paths to this vertex, 1 path to that vertex, 2 paths to that vertex like that, 1 path to that vertex, and 1 path to that vertex. Now that seems kind of clear from a picture because I just drew it, so that's probably compelling. How might I try to prove this in general? So we know that for a standard ST flow, I can decompose it into paths. You guys did that for your homework. How do I know I can decompose a preflow? Yeah, okay, so we can try to treat all the endpoint vertices as sync. Is there like a trick to make that almost automatic? Not quite what I had in mind, but I like the idea of like doing a graph transformation. Oops. Here's what we can do. So given something like this, for every intermediate vertex, we can introduce an extra auxiliary edge. So I can add a fake edge. Let me do a different color, do purple. Okay, like from that vertex was capacity 1. right? So I'm just going to add shortcuts from every vertex to the sink with capacity, say, equal to the excess at that vertex. This will have capacity 2, right? And this will have capacity 1. Okay, so I've added some auxiliary fake edges to the graph that just takes a direct shortcut from every vertex to the sink. And then I can take the flow and I can extend it using these fake edges. Okay, so I extend it using the fake edges. Right, so now I have a normal ST flow. For every vertex, what goes in is what goes out because whenever there was excess, I just added a fake edge to the sink and I just sent the flow directly to the sink. Right? Now you can take this and you can apply that thing you did for homework. And the thing from homework will break this down into a bunch of ST paths in this fake graph. And then if you delete those fake edges from those paths, then you'll get this path packing. Okay, so we can add fake edges, extend it to an ST flow, get the path packing, remove those fake edges. Okay, fine. That was probably the most boring lemma. Okay, so that was a lemma about pre-flow. Here's a lemma about labels to help us understand what's going on with these labels. Okay, so I'm going to let dxy denote the distance from x to y in the residual graph, like number of hops in a breadth first search kind of way. Okay. The claim is that for any two vertices x and y, the level or label of x minus the level or label of y is at most the distance from x to y. Okay. So the question is, why? Right, so I can try drawing a picture. Right, so the interesting case is when the level of x is bigger than the level of y, because in the opposite case, it's a negative number, so the inequality comes for free. Okay, so this is some x, and this is some y, right? And the level of y is less, like, I don't know, maybe this is like 2, and the one up here is like 20 or something. Okay. So the claim is Lx minus Ly is at most a distance from x to y. The question is why? Oh, perfect. Okay, so let's say there is some path, from x to y, right? Okay. When an edge goes forwards, it can only go forwards, it can only go down and forwards one layer at a time. Okay, so to get from, in this example, layer 20 to layer 2, it has to take at least 18 edges to get across the layers. It might do more than 18 if it goes down a while and it goes back up and then goes down and goes back up. But when you're going down, you can only go one step at a time. Okay, so to go from level 20 to level 2, you have to take at least 18 steps. Okay. All right, so in that sense, these labels are sort of like a surrogate for distances. There's some, we label them and we manage them, but they're closely connected to distances. Okay. All right, so one thing kind of interesting about this simple lemma about labels is, remember, the source is always at level n, right? Because initially I saturate all the edges from the source and I put it right at level n, and the sink is always at level 0. Okay, water is gradually going down to the sink. All right, so our lemma says that the distance in the residual graph from S to T, okay, is at least the level of S minus the level of T, which is n. Okay. Now, why is that sort of odd? What's the maximum? Yeah. Yeah, the longest possible path from S to T has n minus 1 edges. Okay. So if it's at least n, then in fact there is no path from S to T in a residual graph. Okay, so actually this algorithm has a property that at any point in time, there is no path from S to T uh, in the residual graph. All right. Okay. Good. Um, okay. In particular, actually, because S is so far away from T, there's always some layer in the middle that's empty, right? Because there's S, T, and there's n minus 1 layers in the middle, but only n minus 2 vertices. So there's always one empty layer, which gives a candidate for an ST cut. All right. All right. Here's another lemma, but this one you guys might be able to guess. Okay. For every vertex V, if V is active, then its level is at most like 2n, or is strictly less than 2n. Okay. The claim is that if I have some vertex V, uh, right? If I have some vertex V, and V has, some excess flow, then, here's layer 0 or something, and I guess here's layer n, so S would be here and stuff like that. We're saying that the layer of V is at most 2n. All right. Why is that? Yeah. Yeah, well, you're really close to the main idea, but it's not quite. Yeah. Oh, okay, good. Perfect. Okay, I think it all comes together. Okay, so the main thing is, okay, so what we previously showed is that that preflow I can break down into a bunch of paths. That includes, in particular, if V has excess flow, some path from S to V. Okay, so which sort of makes sense. You start at the source and you're pushing flow, right? And now V has somehow accumulated some flow. So there's some flow path, that sequence of edge pushes, that gave V the path, the flow. Okay, so if there's a flow path, okay, so that means that S is sending some amount of flow to V, right? That means in the residual graph, right, there's flow going from S to V. So in the residual graph, there has to be a path from S back to V, right? So that means in the residual graph, there must be some path, reversing all those edges with flow on it, right? Because I can always push back flow. Okay, so if I'm sending flow from S to V, then the residual graph must have reverse edges from V back to S. Okay, so in particular, the distance from V to S should be at most n minus 1 or something in the residual graph. And S has level n, and so n plus n minus 1 means V can have level at most 2n minus 1. All right, so, okay, so that means this is good, right? Because when I'm worried about running times of this algorithm, one of the things I'm concerned about is like, oh, can't I just like keep pushing labels up and up forever? Right? It's not clear that like you stopped and there's some ceiling. But what does this lemma tell us? There is a ceiling, because I'm only worried about the active vertices, right? Those are the ones I'm relabeling, the ones that have extra flow. But it's saying, oh, you'll never relabel path 2n minus 1. So vertex only gets relabeled like n times. That's not obvious from the beginning description of the algorithm. Okay, so there's actually a limited number of relabels. Okay. All right. This is one number I want to make sure I do correctly. Well, okay, maybe I don't need it. Okay. Okay, so this is about the question of how do I know the algorithm is correct? Okay, so in our example, it happened to terminate as a max flow, but it's not at all obvious this should happen in general. So, okay, so in general, you have some pre-flow and you have some levels, right? And they're all obeying all these rules that we have set up. And okay, so the claim, sorry. All right, the claim is that if F is actually a flow, not just a pre-flow, but a flow, so all those intermediate vertices have no flow left, which is sort of like how our algorithm terminated. We got pushed all the flow back to S or T. Then there's two claims. One is that F is a max flow. Okay. And the second is that there's some empty layer, okay, in between S and T, and that the part above and the part below gives you a minimum ST cut. Okay. All right. But we can start with part one. The claim is that if it's a flow, so we've gotten rid of all the excess from the intermediate vertices, then it's automatically a max flow. Why though? Well, not necessarily. So if we go back to, because the suggestion was because we've used up all the edges leaving S, but actually by the end of our algorithm last time, because I had pushed flow back into S at the end, I got some of those edges back, right? Because I had eventually pushed 99 units of flow back from X to S. So actually some of that edge came back. Yeah, so if this algorithm ever reaches a point where the preflow becomes a flow, why is it a max flow? So it's down here. Okay. All right, this is a little subtle. Okay. So F is a flow. That's good, right? We want a flow. Okay. In the residual graph, okay. So like think about it this way. Now that F is a flow, right? We're sort of like, I could like, for example, start writing the augmenting path algorithm from there. It's as if, we took a shortcut or something, right? But what would the augmenting and path algorithm do? It would look for a path from S to T in the residual graph, right? And if it doesn't find one, then it terminates, right? So we terminated when we couldn't find any ST path in the residual graph, right? That's how the augmenting path algorithm worked. So what happens if I ran the augmenting path algorithm on our preflow, which had become a flow? Interesting echo. Okay. The S had label N and T had label 0, which told us what about the relationship between S and T? Ah, there is no path from S to T. So the algorithm is always maintaining the fact that there is no path in a residual graph from S to T. So if F becomes a flow, then you have a flow from S to T where there's no augmenting path in a residual graph. So we can appeal to the exact same arguments from that Ford Fulkerson lecture weeks ago and say, oh, that means we're done. Okay. All right, so the next claim is that not only do we have a max flow, but we have a cut um, induced by one of the empty layers. So first of all, if S is at layer n, sorry, and T is at layer 0, right, then there's just not enough vertices. There must be some layer that doesn't have any vertex in it, right, as some index I, and there is no vertex in this layer, right? There must be an empty layer in the middle because there's n minus 1 layers in the middle and there's only n minus 2 vertices out there, okay? And the claim is that all the vertices on this side and all the vertices on that side will give you 2/2 of an ST cut. Okay. Okay, so what do we know? Okay, so there's some vertices on one side, vertices on the other. Okay. I know that like originally somehow I'm sending, okay, whatever's the total size of flow is kind of going across from one side to the other. Right? Because it's coming out of the S side, it's all going to the T side. That we know. Okay. All right. Here's one question. Can there be any edges in the residual graph from one side to the other? No, why not? Because then it would have to go across 2 layers because of the empty cut. Okay? So that means all of the edges that are leaving this side and, let's say from the input graph, which I'll draw in green, all of the edges that went from one side to the other, right, must have been all used up because there's no edges left in the residual graph because you can't jump over 2 layers. Okay, so I've used up all the edges from the S side to the T side in the residual graph, so that's your cut. Okay. All right, so that's it. Okay, so that is that at least explains why the algorithm, if it terminates, is correct. Okay, so if you reach a point where it's a flow, it's not just a pre-flow anymore. It's a max flow because there's no S to T path in a residual graph. And not only that, but if you want to extract the cut, you just have to find one empty layer because you know the edges can't hop 2, and then one side will give you 1/2 of the cut and the other side will give you the other. Okay, so it's like a completely crazy algorithm, right? Somehow, like, something's very clever is going on with these labels, right? Like, somehow these things are just kind of falling out magically. Okay. Okay, so that's why the algorithm is just terminates when there's no active vertices left, because when there's no active vertices left, that means you have a flow, not a besides just the pre-flow. And you have a max flow and you're just done. Okay, good. So that's why, right. Okay. So next we gotta do the running time, and this happened last year too. This is the part that's supposed to use amortized analysis. We only have 15 minutes left. Okay. That's all right, as long as we have fun. Okay. All right, so now we know that if the algorithm reaches a point where there's no active vertices, it's at least correct. It outputs a max flow, it outputs a minimum ST cut. That's great. Next, I want to argue that as I do all these individual pushes, I'm only doing a limited amount. So what we're going to end up doing is we're going to count the total number of times I do a push and the total number of times I do a relabel. Okay, we're going to try to account for those. And then otherwise, it's pretty easy to see that like it's pretty easy to implement these steps pretty quickly, right? Like you just have to quickly identify an active vertex. So you can just keep a list of vertices that have excess flow. And then you just need to know if there's an edge that's going down, you can make some lists and stuff. So I'm just assuming everything else takes constant time. And I'm just going to try to bound the total number of pushes, the total number of relabels, and leave it up to you to think about how to use, linked lists and stuff to do this pretty quickly. Okay. Okay, so we're going to try to account for the number of pushes, the number of relabels. Now, an important thing to do is to actually distinguish between two different kinds of pushes. So when I'm pushing flow out from a vertex, I try to push as much as possible, right? That's one of two cases. One is I use up the entire edge, the capacity of the edge, or I use up all the flow that's sitting at the vertex. So those are our two cases. So the first kind, I feel like, I don't know who gave these names. One is called a saturating push. You use up all the capacity of the edge. The edge will disappear from the residual graph. And if it's not a saturating push, it's called a non-saturating push because we have great names. Okay, so this also means that it must use up all the flow at the vertex instead. Okay, so two kinds of pushes. Okay, so we're gonna try to bound the number of relabels, the number of saturating pushes, and the number of non-saturating pushes. Okay. All right. This we kind of went over first, so I think you guys should be able to guess it. I want to argue that the total number of times we relabel any vertex is at most n squared. Why? Zero, yeah. Yeah, the maximum was 2n, and they started at 0. So a single vertex can only get relabeled like 2n times or something like that. So n times n, and you get n squared. Okay, good. That one's the simplest one. Okay. Saturating pushes. So this means I push so much flow, I use up all the capacity on the edge. The claim is that we have at most m times n saturating pushes. Why? I'll give a hint. Really, the claim is that I'm only going to do a saturating pet for a single particular edge, as it kind of moves around. I'll only do a saturating push n times. So that's when you use up the entire capacity of the edge and you remove it from the residual graph. I'm claiming that can only happen to a particular edge about n times. Yeah. Yeah. So this is similar to other arguments we've had. So if I'm pushing from U to V, right, and I went push down flow, and now the whole edge is used up. So it's going to disappear from the residual graph. The only way for the edge to get reintroduced is if I push flow from V back to U, right? So originally I have U, I have V, and I push so much flow that this gets deleted from the graph and I add V to U back in, right? And the edge from U to V will only come back if I push some flow back from V to U. But in order for that to happen, since I can only push flow down one level, V has to go up above U. Okay, so That means next time U to V comes back, it's gone up. So every time, it reappears, it must have gone up. And again, the maximum is n. Okay, so you can charge it to relabeling the endpoints of the edge. Okay. All right, so these arguments are sort of similar to actually the Edmonds-Karp style arguments. Although it's, yeah, coming from this crazy system. Okay. All right, last one. The number of non-saturating pushes is at most mn squared. This one's tricky. I'll give you guys a chance to try though. Any ideas? Yeah. A little louder. Yeah. It's the last part and we haven't done any amortized analysis yet. So we'll try that. So this is the pedagogical point of the class. I guess the real point is to draw fun pictures. But anyway, all right, so we're going to invent a potential function, right? Here's where things get, I think, really creative. I'm going to sum over all the vertices that are active. The level of that vertex. Okay, so for every vertex that has excess flow, if it's at level 10, I add 10 to the potential. If it's at level 20, I add 20 to the potential. Okay. All right, so at the beginning, all the vertices are at level 0, so initially the potential is 0. Okay, so let's see what happens with each of the operations. So suppose I do a relabel, right? How much does the potential change? Okay, will be 1, right? So level 10 goes to 11, so the contribution goes from 10 to 11. Okay. All right, how about a saturating push? So I have some flow at a vertex, and I send some flow to another vertex. We just want an upper bound. It doesn't have to be great. How much could the potential go up by? 0? Why? Yeah, but okay, so imagine I have like 10 units of water here, and this edge can only carry 5. So if I push 5 down, this vertex will end up with 5, and it'll still have 5 up here. So n. So you might, take a vertex that's not active and make it active, right? Because I've taken some water and I've pushed it to something that didn't have any water. Now this is active, and the level was at most 2n or something like that. So, okay, so you might activate an inactive vertex, so this will go up by at most 2n or something, or n between friends. Okay. All right. Okay, so that means, by the way, the total, let's see. Okay, so do you guys remember how many relabels we might have at most? N squared. So the total increase in the potential from relabels would be? Okay. One clear answer is like way better than 100 whispers. Okay. Um, Same with saturating pushes. Do you guys remember how many saturating pushes? Mn. So then the total increase from saturating pushes is? Yeah, like mn squared or 2mn squared. All right, now let's look at non-saturating pushes. This is the thing I want to bound, right? What happens to the potential when I do a non-saturating push? That means like if I had like flow 10 at a vertex, I push all 10 units of flow, down to some other vertex, right? What happens to the potential in sort of the worst case for us? Sorry? Increases? Decreases, right? So in the worst case, maybe this didn't happen. So I pushed like 10 units of flow from here to here. This goes to zero. So this becomes inactive. Say this is at like level 20. And it goes to some vertex at level 19. And maybe this becomes active. So you subtract 20 from the potential, and then you give back 19. So you have a net decrease of at least 1. If you're lucky, maybe this vertex already had potential, in which case you just go down by 20, but we can't hope to get lucky. So the change in potential, it goes down by at least 1. It might go down by more, but at the very least you get to go down by 1. So the total increase from other operations is roughly mn squared, right? And meanwhile, each non-saturating push will go down by 1. So what does that say about the number of non-saturating pushes? Potential is also always non-negative. Sorry? Equal to what? Mn squared. So I mean, like think about I don't know. There's like an elevator, right? And then if I told you, oh, the elevator, as it goes up and down, went up a total of like 1 million levels, and then I ask you, oh, what's the total amount the elevator might have gone down by? Right? It's almost a million because it can't go under the ground, right? So, okay. All right. So the maximum amount it can go up by total is mn squared. Each time you do a non-saturating push, it goes down by at least 1. So you can only have at most mn squared non-saturating pushes. Okay, and that was your amortized moment of the day. All right. Great. So we add all that up, and the bottleneck is these non-saturating pushes. And so you get mn squared running time, which I think is better than what we got for Edmonds carb. Right? That was m squared n, wasn't it? It wasn't? Oh no. Yeah, when you shake your head, I don't know if that means yes or no. Okay. All right. Okay. All right. So Edmonds squared. I think Edmonds carb was m squared n because roughly each edge went up n layers. You have to do a breadth first search. Okay. All right. Now the next question is, can we do better than mn squared in the next 2 minutes? Okay. All right. So the bottleneck is just those non-saturating pushes. The pushes where I'm pushing all the flow out of a vertex, but I'm not using up the capacity of any particular edge. So we're going to try to get that down. Okay. So in general, there's a bunch of different, types of push-relabel algorithms, and we're just going to study one, which I call top-down push-relabel. Sometimes it's also called maximum label or highest label push-relabel. But you have many vertices out there that have extra water at any point in time. The idea is to choose the highest one. So always choose the highest one. That's the only rule. Okay. And we're going to try to get a slightly better bound for this. Okay. So the previous lemma stuff all still apply, right? Because previously we just didn't assume anything. So the number of relabels is still at most n squared. The number of saturating pushes is still at most mn. And the number of non-saturating pushes at most mn squared, but we're going to try to do better. Okay. All right, so the claim is that the number of non-saturating pushes is at most n cubed. In fact, we'll show that for any particular vertex v, the number of times I do a non-saturating push and kind of dump all the flow out of v is n squared. And then n times n squared will give you n cubed. Okay. Anyone want to guess why? So I picked the highest active vertex, right? And I've pushed all the flow out of it. So this used to be active. It used to have extra flow. All the other active vertices are lower. And now I've pushed all the flow out of it and there's no flow left up above. What has to happen for this one to become active again? Yeah. Yeah, so in order for this thing to get water again, another active vertex has to move above it so that it can push water back down. So in order for this vertex to get any flow back, some other vertex has to get relabeled at least once. And what's the total number of relabels? N squared, I think someone said. I'm not sure. So, okay, so there's only n squared relabels, so you can only have n cubed non-saturating pushes when you're always picking the top vertex. Okay, nice and simple. All right, can you do better than n cubed? Right, n cubed is now our best running time. We're making improvement. And in the remaining 0 minutes, I want to try to argue that we can get it down to n squared square root m, so even better. Okay, n squared square root m. Okay, I know that once we run out of time, you guys don't want to guess anymore, so let me just go through the proof. Okay? Okay, so we're going to define a funkier potential. Okay? This is summing over every vertex v. How many, so here's an active vertex v, it has some water. How many other active vertices are there at the same or lower level? Right, so there's 100 vertices lower that are active. Oh no, just how, if there's just 100 vertices lower, then it'll contribute 101. Okay. All right. So that's the potential. It's a little more complicated than last time. Okay. Now, if you do a relabel or a saturating push, so if I take an active vertex and I relabel it up, now there might be a lot more vertices at the same level or lower. Right? So a relabel might increase the potential by n. Okay. Likewise, if I do a saturating push, so I take this vertex and I push some water out to another vertex, this vertex becomes active, and there might be at most n vertices underneath, so the potential might go up by n. Okay, so for either of those operations, the potential might go up by at most n. Okay, so here the potential now goes up by a lot for these operations. The total increase is mn squared. Okay. Now we just need to look at the non-saturating push. So if I'm pushing at a vertex v, right, and I do a non-saturating push, it's going to push water down and itself it's going to become inactive, right? So how much is the potential going to go down by? Well, any vertex that's at the same level is not going to be counted by that new active vertex down below. So at the very least, the number of vertices at the same level will be the decrease in the potential, right? So I have a bunch of flow. I push the flow down. This has no flow left. And so this vertex might be counting all the vertices underneath, but it's leaving out the vertices that were at the same level. Okay, so that's the decrease. All right, let me try to keep going quickly. What we're going to do is we're going to say that if there was a lot of vertices at the same level, I'll call it like a really big push. And if it's relatively small, I'll call it a small push. Okay, we'll choose some parameter k at the end to delimit what's a big non-saturating push and what's a small non-saturating push. Almost done. And we'll have two claims. One is that there's at most mn squared over k big pushes. The other one is that there's at most n squared k small pushes. And then you just choose k to balance the terms, which in this case is square root m. So let me quickly do these two claims, if I can remember. All right, this is the more fun one. Okay, so a big push is when you have a lot of vertices on the same level. Okay, at least k. And the claim is that there's at most mn squared over k big pushes. The question is why? I'm at a vertex v, I push all the water out, and you had tons of vertices on the same level, at least k. So the potential goes down by at least k. And how big could the potential be? Mn squared. So big pushes will decrease the potential by more. So you have at most Mn squared over k, big pushes. Okay. All right. Uh, all right. How about small pushes? So small pushes, like imagine, oh, here's a vertex V and there's only like 5 other vertices at the same level. Okay. All right. So the claim is that there's only n squared k small pushes, but really what's going on is imagine the highest level is like level 100, right? The highest level was active vertices, I mean. Okay, so that means you're pushing out of vertices at level 100, right? Until there's none left, and then you go down to level 99 because you're always picking the highest level. So each small push, right, is going to take one of these vertices and get rid of all the flow underneath. So originally there's at most k of these active vertices, because there's at most k vertices at that level. Okay. And each iteration, you get rid of one, you get rid of one. So you can at most have k until you've used up all the vertices at that level. Okay. So after k consecutive small pushes, the highest active level has gone down. It has gone down, has gone down, has gone down. And, right. So if we call that like a phase is like one stretch where the highest active level is the same, right? The claim is that there's only n squared phases. This is just because they can only change when you relabel and relabel or something like that. Okay, that's good enough. We'll finish it there, and that's all I had. Okay, so with slightly more cleverness, you can get n squared square root m, and that's that. All the details are in the notes. All right, thanks, guys.